Welcome to Biology My Passion. I am Soumya Harikrishna. We will learn a chapter in physics, that is magnetic effect of electric current. We are all fascinated about magnets. If you get a magnet, we usually try certain things out, right? First, we will take a small pin or a paper pin and we will attach to the magnet, and to that we will attach another one. To that we will attach another one. Maybe 3, 4 we can attach. After that it will not stick. That means what? The strength is reducing. So around a magnet there is an area where the force of the magnet can be experienced. The same way we try to look at the bringing another magnet near it. Sometimes it may repel, sometimes it may attract. But you know what is the reason? Magnet, especially bar magnets, they have got north pole and a south pole. So you know that north pole is actually pointing towards the north pole of the earth. That is, if you simply tie a string and you hang one bar magnet means a magnet in the shape of a bar, and if you just hang it with a string, it will point towards the north pole of the earth. That end is the north pole of the magnet, whereas the end which is pointing towards the south of the earth will be the south pole of the magnet. Okay, so and most of the magnet when we take, it will be marked the north and the south poles. So here we know that like poles attract and unlike poles repel. But in this chapter, we are not talking about the natural magnets. We are talking about a current carrying conductor having magnetic property. About electricity, we learned in the previous chapter. So, electric current, when the current is passing through a conductor, the conductor acts as a magnet, or it has got some magnetic property. About that, we are going to study, that is called electromagnetism. So you know that this was first actually observed by a scientist called Oersted. If you bring a compass needle near a current carrying conductor, you can see that the compass needle is deflecting. Actually, the compass needle itself is an example of a magnet. So one magnet getting deflected, that means it is in the vicinity of another magnet, right? Otherwise the magnet cannot deflect. So compass needle is deflecting means there is another another magnet near it. So current carrying conductor is acting as a magnet. But if you switch off the current, will the deflection happen after that? No, right? So as long as the current is passing, the conductor is acting as a magnet. Suppose if you see in the conductor, plus and minus, so like this. So this is north, current is coming from here, north to south direction current is flowing. So that time if you keep the compass needle, you can see that compass needle is deflecting towards east. That is, north pole of the compass needle is deflecting towards east. So this is the north of the compass, this is the south of compass. So if you reverse the direction of current, for example, by changing the battery or cell, we can reverse the current. So this is plus, this is minus. Now the direction of current is from south to north. So in this case, we can see the deflection of the needle of the magnet also, compass needle also changes. That is, it is now becoming here north, south. So that is, it is towards the west. So north to south, if the current is passing, deflection of the compass needle is towards the east, and if it is from south to north, it is towards the west. Okay, so by changing the direction of the current, we understood the direction of magnetic field is also changing. So now I told a word magnetic field. What is that magnetic field? Suppose this is a magnet. Around the magnet, the field magnetism can be experienced. That's what I told. If you attach a pin, then another pin, maybe 3. After that it is not attaching. So the magnetic field is only till now. So around the magnet, all around the magnet, that area in which the force of the magnet can be experienced. If you bring something to that area only, it will attract, right? So that is called a magnetic field. But magnetic field, we have tried to map the magnetic field using iron filings. So if you keep a bar magnet on a white paper and if you dust some iron filings on it, you can see that they arrange in the form of circles. So from that we get that this magnetic field is in the form of concentric circles. So that we can call them as magnetic field lines. When you are drawing the magnetic field lines, you have to know about the properties of the magnetic field lines. The first property of a magnetic field line is it always goes or starts from the north and it ends in the south. So from north to south pole. Direction of magnetic field lines is from the north pole to the south pole. Okay, and how do we mark it? Suppose there is a magnet. So this is north pole, this is south pole. You have to bring a compass needle. We know that compass needle will deflect showing north direction here. So wherever the north of the compass is showing, there we will put a dot. Now we will displace this compass needle from here and keep at the north of this. So again deflection will happen. So everywhere we keep marking the north pole, and you can see that the north pole is getting attracted to south pole here. So if you connect these dots, we will get a circle. So like this many we can draw. Next position I am keeping here. So I will get here. So the direction you have to mark, that is very important. Or this side I can get like this. Another one like this. But here what is the direction? North to south, always north to south. Then a few can go straight also because they are long, the bigger ones. So here we are showing just as a half only. We cannot draw all. So we show as like this only. Here all coming in. Okay, so the direction of the magnetic field lines is from north pole to south pole, and inside the magnet it is from south to north. So inside from south to north pole. Okay, so it forms a circle because it has to be a circle, means inside also it has to pass. So here it is like this, inside also it is passing. So they are forming circles called a concentric circle. What are concentric circles? Means one outside, another one, outside, another one, outside, another one. So that circles are called a concentric circles. Now the most important feature that you have to learn here is no two field lines intersect each other. When I drew also, I did not crisscross them. Okay, they cannot intersect each other. Why can't they intersect? For example, imagine this one. Each one we are drawing with the north pole of the compass needle. Suppose it is crossing here. Okay, maybe this is the first cross. If you see, when I keep the compass here, which direction is north, there only I am showing the direction. So the compass needle is showing this direction, means the line will come here, and compass needle is showing this, means the line will go there. But it cannot be two different points from one compass needle. Compass needle can show only one direction, right? So if it is crossing, means at that point the compass needle shows two different directions. That is impossible. So this is an important point, and also why is another important question that you should know. The next point is fifth one. They are crowded at the poles. You can see the lines are mostly crowded at the poles. That means the force or magnetic force or strength is maximum in the poles. As I mentioned earlier, in this chapter we are discussing the magnetic effect of only current carrying conductors. But these current carrying conductors can be of different shapes. In this chapter we are discussing three different shapes of current carrying conductors. If the current carrying conductor is straight, how is the magnetic field? If it is circular, how is the magnetic field? And if it is a solenoid, we will talk about solenoid, it's like a spring. That is how will it be? That these are the points that we are going to discuss. So let's start with the first one. If it is a straight current carrying conductor. So straight current, suppose this is a conductor and I am connecting it to a battery, positive and a negative. So we know current is going in this direction. So north pole to, it is coming to south pole. Current is coming from here, right? So north to south. So if I am inserting a cardboard box here, and if I put the iron filings around this, there will be concentric circles which represent magnetic field lines, right? These concentric circles are representing magnetic field lines. Okay, so now in this picture you can see when the current is going from north to south, the magnetic field lines are going in a clockwise direction. Like the deflection we talked about before, when we change the direction of current, we saw the deflection also changing. The same way here, if I change the plus and minus here, positive and negative terminals here, then the current will flow in the opposite direction. That is, it will go from south to north. Okay. Now, will there be any difference in the direction of the magnetic field lines? This all will go from this anti-clockwise direction. So, when we change the direction of the current, the direction of the magnetic field lines also change accordingly. Now here from each point on the conductor, any place we keep, we can see that from that particular point concentric circles are forming, and farther away they are becoming weaker and weaker, right? So now we have to find out how can this direction be determined. That is, sometimes you know only the direction of current. How will you find out the direction of magnetic field lines? Using a straight current carrying conductor. We are using a rule that is called the Maxwell's right hand thumb rule. So this is my right hand and this is a thumb of my right hand. So you have to hold your hand in such a way that your thumb is pointing the direction of the current, whereas your fingers will point the direction of the magnetic field lines. For example, we will see this condition. So imagine this is a straight current carrying conductor. What is the direction of current? North, south to north, means upward. So I am holding this current carrying conductor in such a way that the current is going upward because my thumb is pointing upward. So south to north it is going. Now what is the direction of the magnetic field lines? It is going, because it shows the direction of my fingers, you have to see from knuckles it is going this way, right? So this is called the anti-clockwise direction. Okay, so when the thumb is kept in the direction of current, the fingers will show the direction of the magnetic field lines. Now if I hold like this, suppose the current is from north to south, I can see the circles are coming in clockwise direction. The same way, if current is going into the paper, okay, or into the board, I will be holding like this. So it is going like this. Whereas if I am holding this way, it will be coming like this. From downwards, it is coming like this. Okay. So different positions we have to see the current carrying conductor. Or if I am holding like this, that is from, this is west, that is east. West to east, it is coming like this. Suppose I change east to west, then the direction also changes. So every possibility we have to know. Each time we have to hold our thumb in the direction of current so that the fingers will point the direction of the magnetic field lines. Here we have to learn one more point. So the main point here we have to learn is the Maxwell's right hand thumb rule. This rule is otherwise called the Maxwell's corkscrew rule. You know that there are screws we are all familiar with. The screw has got a kind of a spiral rings wedge over it, right? So when we are putting a screw into a cork or any place, we are turning it so that it will go inside. So if you are holding the screw in the direction of current, in which direction we are turning it to put it inside, that is the direction of the magnet. Whether we are turning it clockwise or we are turning it anti-clockwise, it will be similar to this law only. So it is otherwise called a Maxwell's corkscrew rule. Now, in one more point we have to learn here, that is what are the factors on which the magnitude of the field here depends. So magnitude means what? The strength. Magnitude depends upon two factors. One, the current passing through it. That is, it is directly proportional to field strength. So, if more current is passing, then more field can be experienced. So, if I want to increase the force, magnetic force here, or strength of the magnetic field, I have to just increase the current passing through that conductor. Second, we know that as it is closer to the current carrying conductor, it is stronger. When it is moving away, it becomes weaker. So second, distance from the conductor, it is inversely proportional. That is, when it moves away from the conductor, the field strength decreases. So remember, there are two factors affecting the magnitude of the magnetic field. One is the current. As the current increases, field increases. Current decreases, field decreases. Distance, when it is closer, it is more. When it is moving away, that is, distance increases, field strength decreases. Next, we have to discuss the magnetic field in a circular current carrying conductor. So imagine this is a circular current carrying conductor, and through this I am conducting electricity. That means to end of this can be connected to a battery so that the current will start passing through it. So we know that when the current is passing through this is acting as a magnet. So each point on this ring will be forming concentric circles. So 1, 2, 3, 4, like that. So when the bigger ones are forming, in the center they appear as straight lines, because these are all small like concentric, but when it comes to center big circle, so they will appear almost straight. So like that, imagine from each point, different points it is forming, so all of them will be forming straight lines in the center, making this part very strong. Okay, so this is how the current is passing through it and making it a field, means a magnet. So here also the direction can be changed. Suppose I change the direction of current, direction of the circle also will change. This we can find out using the same rule, right hand thumb rule. Suppose the current is going from here, I will hold it like this. Now the field lines are like this. Suppose the current is going this way, then the field lines are in the opposite direction. Okay, but here we have to learn what are the factors influencing this magnitude in the magnetic field inside the circular loop. First, as we explained earlier, current. Current increases means what? We can increase the magnetic field in it. Magnitude can be increased by increasing the current passing through the loop. Now, second, there we learn in straight conductor about distance, because when we move away from it, the distance increases, the strength will decrease. But here we cannot move because it's a closed circle. But we can say that here when the radius is increasing, instead of this circle, if I am taking a bigger one, so the outside circles will be far away. So naturally they will be weaker. So it is inversely proportional to the radius. So when we increase the radius of the loop, then the strength also becomes less. Okay, so a small coil or a circular loop will have more strength than a larger one, that is towards the center. Now there is one more thing affecting here. Here three factors are there. Third is the number of turns. Here I am using only one circle. Instead of that, if I take all these together and keep those many number, it is multiplied like into n times. N turns if I keep, strength also will increase n times. So magnitude of a field line can, or magnitude of the magnetic field in a circular current carrying conductor is directly proportional to current, directly proportional to the number of turns, inversely proportional to the radius. Suppose if you want more field, you can increase the current, you can increase the number of turns, and if you want less, you can increase the radius. The third current carrying conductor we have to study is in the shape of a solenoid. Solenoid means it is a circular structure, means the insulated copper wire, if you are wrapping in the form of a cylindrical structure with a many turns. It's just like a spring, we say. Some ballpoint pen and all, we have the spring inside, right? The same way it is but here it is a insulated copper wire we are using. And in that both the ends you can connect to the battery, so that current will start passing through it and it will act as a magnet. But solenoid usually acts as a bar magnet. Okay, so this we are connecting to a battery, positive, negative, and you can see that it acts as a bar magnet, similar to a bar magnet. That is, this is north pole and this is south pole. So now we know what are the characteristics of the field lines as we discussed in the beginning. They are from the north pole to south pole as concentric rings. Inside it is from south pole to north pole. But inside all these lines are parallel. That means inside they have uniform magnetic field. The strength is uniform throughout. Inside a solenoid, anywhere you keep, the same force you will experience because it is uniform. Why? Because the field lines are parallel inside. So after passing current through it, we know that there is a uniform magnetic field experienced inside this. During that time, if you keep a magnetic material inside, you can make an electromagnet. So usually we use a rod like a soft iron rod. Soft iron is the best material we can use for this. And if you insert a soft iron rod inside a solenoid and pass electricity through it, it will act as a very strong magnet. But as soon as you switch off that, it will stop. Why are we not preferring steel? Because if you use other magnetic materials like steel, it will retain the magnetism, or it will act as a permanent, it will turn into a permanent magnet. So there is no comeback. But electromagnets, the advantage is often if you use, as soon as you switch on the current, it is acting as a strong magnet. The moment you switch off the current, it will be natural again without any magnetic property. So this is called the electromagnet, which is usually used in many gadgets that we are using, including our TV, radio, etc. So we have to use this in medical field also. So different applications are there for the solenoid or electromagnets. So now we will see what are the factors in which the field strength depends. So first, as we told about the circular loop, by increasing the number, we can increase the magnetic field. Of course, instead of this, I am taking a coil with a very close turns. More number of turns, then definitely the field will be more, because from each circle it is producing, right? So it will be more. Then current, of course, that we learned in the first two structures. If you increase the current, definitely the field of the magnetic field also will increase. Then third is electromagnet. If you talk about, if you want to make the strength of the material, that means the nature of the material will also determine the strength of an electromagnet. That is, as I mentioned, soft iron if you use, you will get a very strong electromagnet. You know how if it is a bar magnet, we can find out it's a north pole and south pole that I discussed. But if it is a circular loop or a solenoid, how will we find out it's north and south? By seeing the direction of current, we can find out the north and the south pole. For example, if current is in the clockwise direction as I showed now, we can write S like this. So it is going clockwise. The same way, if it is anti-clockwise, it is north pole. I have written N here. This is N, this is S. So south pole and north pole. So if it is clockwise, it is south pole. If it is anti-clockwise, it is north pole. Now we are talking about another aspect called a force. That is, we know that a magnet, if it is, suppose a compass needle, initially we brought near a current carrying conductor, it got deflected. Deflection means it's a kind of force acting on it, right? The same way, as we are seeing in this activity, there is a current carrying conductor which is hanging down, okay, in that current is passing. So as soon as the current is passing, it has a magnetic field around it. But we are bringing another magnet, a horseshoe shaped magnet near it. So definitely there will be a force acting on it, and that force, if is enough to deflect it, provided it is not fixed. Here you can see it is hanging, so it is easy to move so that the deflection can happen. So when we change the direction of current or direction of the magnetic field, we can see that the direction of force also changing. So till now we have been discussing only two aspects, current and magnetic field. Now we are bringing the third aspect, current, magnetic field, which can exert a force. But for this force to act, all the three, the current and field, should be in a perpendicular direction. Only then we will get. Okay. So to find out the direction, so here if we are passing the current through A to B, then the deflection will be to one side. If we reverse the current, the deflection will be to the other side. So we understood with the current what will happen, the change in the direction of the force is happening. The same way, if you turn the north and south pole of the horseshoe magnet we are bringing, first is suppose north is on top, deflection is to one side, south is now tilted, then it will change. So there, because of field also the force is influenced. So here, as I mentioned, remember these three should be, the magnetic force is perpendicular to the current, direction of current, perpendicular to the direction of the field, but only when it is perpendicular to the field, the maximum force is exerted. If it is parallel to the field, the force exerted is zero. Okay. Now we can use a Fleming's left hand rule to find out this. So initially we studied right hand thumb rule, that is different, that is Maxwell's right hand thumb rule. Now we are learning Fleming's left hand rule. In Fleming's left hand rule, we are using three fingers. This is our first finger is thumb finger, then this is the index finger, and the third is our middle finger or the central finger. That means I will tell you why. So thumb finger, when we are taking, thumb has got M in it. When you write thumb, it has M in it. M stands for motion or force. Okay, so thumb is the direction of force. Then this is forefinger. Forefinger has F in it. It starts with the F, so it is the magnetic field. Don't take F for force. Okay, here it is magnetic field. And this is, instead of middle finger, we are representing this as a central finger. So the central finger, C for current, we can say. Central, if you pronounce, then C for current. So all the three directions we got, the three are in perpendicular to each other direction. So these two are perpendicular, these two are perpendicular, these two are perpendicular. So this is motion or the force. This is the direction of the direction of the magnetic field, and this is the direction of the current. So if you know the direction of the current and if you know the direction of the magnetic field, you have to adjust in such a way that the thumb will point to the direction of the force, which direction the force will be exerted. Okay, but here only thing is that when you are doing this, don't change it like this or this or this. Don't change your finger. First you hold your finger like that. Don't change it. Rest all changes should be made with your entire hand. Okay, or you can do with the wrist only. Don't change anything in these fingers. Fingers are fixed. They are perpendicular to each other. Don't change the position. So when you do the practice questions, you will understand how to find out this or apply this in your examination. So if it, mostly, as I mentioned earlier, it will be on the plane of the paper. If the current is in this direction, that is from east to west, so I'll be keeping like this. Current is in this direction. Then field is maybe towards the paper. Towards the paper means what? I'll keep like this because it is towards the paper. Then where is the force acting? It is outward direction, right? So like that you have to calculate or find out. Hope you understood all the points that I discussed today very well, because these are explained in view of examination. So please thoroughly understand these concepts what I explained. If you like my videos, please like, share and subscribe to my channel Biology My Passion. Thank you for watching.